In part 2 of our discussion, we focused on the quantitative descriptions, the thermodynamics really of water and its properties. Now we're going to transition to a more qualitative discussion, primarily centered on the common interactions, the common non-covalent interactions that you're going to observe in aqueous biological systems. Perhaps the most common non-covalent interaction that we will encounter in this course is hydrogen bonding. So when we talk about hydrogen bonding, which we have already introduced the concept, but when we talked about it previously, it was focused on hydrogen bonding between water molecules. But now we have to think more broadly. When we talk about hydrogen bonding in biological systems, really, less often will we talk about water. More often we're going to talk about hydrogen bonds forming through functional groups found in biological molecules. So the common trait of all of these hydrogen bonds that we're going to talk about are that there are asymmetric bond dipoles. So if I can draw your attention over here to this schematic, you'll see a carbonyl group, and you will notice that there is a dipole. The oxygen in this case is more electronegative than carbon, and therefore it pulls electrons away from that carbon, generating a partial positive charge on the carbon and a partial negative charge on the oxygen. Here you have an asymmetric dipole. This is in contrast to a molecule like, say, carbon dioxide, where you have a central carbon and two oxygens, and those two oxygens are equally pulling electrons away from the carbon. Therefore, the two dipoles cancel one another out, and you have a nonpolar molecule. So here, what we need is an asymmetric dipole that is going to allow for optimal hydrogen bonding. And so these bond dipoles, as I state here, they are common in uncharged polar molecules. You'll see plenty of examples, but the bond dipoles we're talking about, they are what make uncharged polar molecules soluble in water. And this is the same concept that you see for ionic substances going into solution as well. So basically what you have is a charge or a some sort of dipole that allows for hydrogen bonding to occur. Now, in biological systems, you're going to see some trends. You're going to see some functional groups show up more often than others. So, for example, hydroxyls, carbonyls, carboxylates, ammoniums, these are going to show up more often, and it is because they can hydrogen bond very well. If we look at some examples down here of common functional groups, common hydrogen bonding patterns, you'll see, for example, the hydroxyl group here. Don't worry about what the R group is just yet. When we get to discussions of amino acids, you're going to see that there are specific functional groups that show up, but the hydroxyl group in this case can function as a hydrogen bond donor and interact with water molecules that will function as hydrogen bond acceptors, or even form hydrogen bonds with other things within biological molecules. So you can have intramolecular hydrogen bonding as well. This is going to be very important when we talk about non-covalent interactions that lead to stabilization of overall three-dimensional structure. In other cases, you'll see here you have a ketone group. The carbonyl of the ketone interacts with water. In these two cases, we are focusing on interactions with water. However, you're going to find more commonly in biological systems, especially in reference to these intramolecular interactions I've already referred to, you'll see hydrogen bonding between functional groups in the same molecule. So here, for example, you have a carbonyl group interacting with an amide proton, and this is within a single molecule. When we get to talking about DNA, the double helical structure of DNA is stabilized by hydrogen bonding between two DNA strands. So hydrogen bonding is going to be very important, and you will see more examples of this going forward. Let's look at an example. So hydrogen bonding will impact the physical properties of a solution. So a general rule of thumb is that molecules of similar molecular weight are going to have similar boiling points. Now, if we just look here at propane versus ethanol, you'll see that they share very similar molecular weights. Propane has a molecular weight of 44 grams per mole. Ethanol has a molecular weight of 46 grams per mole. However, the boiling points here are vastly different. The boiling point of propane is negative 42 degrees Celsius, and ethanol is positive 78 degrees Celsius. So what's going on here? Why are these two molecules, even though they are of similar molecular weights, why do they differ so dramatically in boiling point when the rule of thumb says that these two molecules should have very similar boiling points? Well, if you look at the two molecules, you'll see one big difference. There is a hydroxyl group that shows up in ethanol that is not present in propane. So this hydroxyl group can participate in hydrogen bonding. I just told you on the previous slide that a hydroxyl group is a very common hydrogen bond donor or even acceptor depending upon the orientation of molecules. So you should notice that the OH group, you're going to have an asymmetric dipole. The oxygen is going to pull electrons away from the hydrogen, therefore generating a partial positive end on the hydrogen and a partial negative end on the oxygen. So the difference here, this OH group increases the boiling point of ethanol 120 degrees relative to propane. So this is quite significant. So we can already see here that hydrogen bonding is going to increase the boiling point of a solution relative to a comparable solution lacking hydrogen bonding. So water is known to have a very high boiling point, and it is because of hydrogen bonding. So if you don't believe me, let me push this idea a little bit further. So if we compare 1-propanol to ethylene glycol, 1-propanol has a single alcohol group, otherwise it's alkane, just saturated hydrocarbon. Ethylene glycol has 2 alcohol groups, very similar molecular weights. 1-propanol is 60.1 grams per mole, ethylene glycol 62 grams per mole. But the boiling point here is different yet again. 1-propanol has a boiling point of 97 degrees Celsius. Ethylene glycol has a boiling point of 197 degrees Celsius. So we see here that a second hydroxyl group further increases the boiling point by 100 degrees Celsius. So the big takeaway here is that hydrogen bonding is going to increase the boiling point, and this is because of increased stabilization of the liquid state via non-covalent interactions. Okay, so if we look at some common biological molecules, you'll see trends that explain why some are soluble in water and some are not. Remember, water is the biological solvent. We are 70% water. So when we look at these things, we have to think about them in the context of an aqueous system. So let's start with the polar side over here. You'll see in this table we have a grouping of polar molecules and a grouping of nonpolar. And if we start with glucose, you should note here that there are a whole lot of hydroxyl groups. Glucose has 1, 2, 3, 4, 5 hydroxyl groups. Hydroxyl groups, as I just told you, can undergo hydrogen bonding. So glucose, it is very soluble in aqueous solution. It is because of the hydroxyl groups. Glycine, this is an amino acid that we'll talk about. Glycine has charged groups at biological pH. It has an ammonium group. It has a carboxylate on the other end. These can undergo hydrogen bonding. So when we talk about hydrogen bonding, we're talking about hydrogen bonding with water. So glucose and glycine are very soluble because they can undergo hydrogen bonding. Aspartate has a similar story. This is another amino acid. Lactate, similar story. Here we have a carboxylate and a hydroxyl group. Glycerol has 3 hydroxyl groups. So all of these polar molecules, the common theme amongst them is that they can easily form hydrogen bonds with the solvent water, with bulk water. And in doing so, they become hydrated, and the ability of water to hydrate these molecules is more favorable than the interaction of these molecules with themselves. Remember, in the previous talk, something is soluble because the solvent makes it possible, basically makes it such that the interactions of the solute with the solvent are more favorable than solute-solute interactions. So the formation of hydrogen bonds here between water and each of these solutes is more favorable than the solute interacting with itself. Now, in contrast, our nonpolar molecules, often what you're going to see are amphipathic biomolecules. And what I mean by that is an amphipathic molecule is a molecule that has nonpolar parts as well as polar parts. So that's a broad definition, but here if we just look at like a typical wax, you'll see later in this course this is an example of a lipid. In this molecule you have two nonpolar tails. So you have a nonpolar hydrocarbon part of the molecule and another nonpolar hydrocarbon part. But there's a carbonyl group right here. In fact, this is an ester functional group. The carbonyl oxygen can undergo hydrogen bonding. So there is part of this molecule that can undergo hydrogen bonding, but the large chunk here is in fact nonpolar and would not be expected to be soluble. And just to remind you, we would not expect this part to be soluble because there are no dipoles. There's nothing, no reason to think that there are going to be partial positive or partial negative charges that accumulate here that would enable hydrogen bonding. So this part of the molecule may interact with water, but the bulk of the molecule will not. There are amino acids that are considered in this way as well. Phenylalanine is a very good example where you have a nonpolar phenyl group here, but you have an ammonium and a carboxylate. So some of this is charged and can form hydrogen bonds, but not all of it. Phosphatidylcholine is another example. This is another lipid very similar to this wax I just talked about. So what I'm getting at here is that common biomolecules will more than likely have polar groups, polar functional groups, but in some cases may be purely polar, so the entire molecule is soluble in water. But in other cases, this may not be true. And as you're going to see going forward, these lipids that have nonpolar parts and separately polar parts, these are going to adopt very unique structures in aqueous solutions that account for and more or less respond to the lack of interactions with water. Before I move significantly into our discussion of hydrophobic interactions, I want to provide some orientation. At some point in your lives, you have mixed something nonpolar with water. This could have been oil, this could be solvent, say benzene, hexane when you're in the lab. Whatever was being mixed, you probably saw that two phases formed. What you should note here is that that is a consequence of solubility. Neither of those liquids is soluble in the other. Your nonpolar solvent or your oil is not soluble in water. Your water is not soluble in your nonpolar solvent. So you see two phases form. Nonpolar compounds like benzene or hexane are hydrophobic. They are water-fearing. As such, they are not soluble in water. They are unable to undergo energetically favorable interactions with water molecules. And as a consequence, they actually interfere with hydrogen bonding among water molecules. So nonpolar molecules are unable to form energetically favorable interactions with water molecules, hence their insolubility. Now, it should be noted that any solute, all molecules or ions that you introduce into solution actually do interfere with the hydrogen bonding of some water molecules. You saw this last time when we talked about ions going into solution. You form a hydration shell, and that hydration shell formation interferes with the hydrogen bonding of water in those solutions, in aqueous solution. But, the big but here is that your polar solutes like sodium chloride compensate for those lost water-water hydrogen bonds by forming new solute water interactions. The net change in enthalpy in this case for dissolving polar solutes is generally small. Hydrophobic solutes, on the other hand, offer no such compensation. Their addition to water may result in a small gain in enthalpy. Remember, when we talk about the free energy equation, you have delta H minus T delta S. So if you see an increase in your delta H, your enthalpy, this actually increases to the unfavorability of a process. So this is very important. The breaking of hydrogen bonds between water molecules takes up energy from the system and requires the input of energy from the surroundings. So in the case of nonpolar solutes going into solution, generally speaking, these are not favorable events. Hence, the formation of two layers when you mix your nonpolar solvent with your water. They don't want to mix together. They are not soluble in each other. The nonpolar solvent is not soluble in the aqueous solution. The aqueous solution, the water, is not soluble in a nonpolar solvent. Now we can turn our attention to the hydrophobic effect. I have at the top here this labeled as hydrophobic interactions. This is the language that your textbook and many other textbooks use, but I really want to highlight that this is not an interaction per se. This is more of an effect. So I will often refer to this as the hydrophobic effect. And this is because there are no direct interactions that occur. No non-covalent interactions occur between water and a nonpolar solute. It's more of an effect. I have labeled the slide here as hydrophobic interactions because I want you to see that this is the language. I want you to become accustomed to the language that your book uses. Okay, so I just told you that a nonpolar solute, it does not readily hydrogen bond with water. However, if I mix a nonpolar solute into water, my nonpolar solute still must occupy space. It has a volume, each molecule occupies a defined volume, so it must occupy space. Okay, so what happens? How does this even, what happens? In bulk solution, if you look at the left-hand side of this figure here, this reflects water molecules in bulk solution. So these water molecules form irregular structures. They are very dynamic. They are moving around. They are entropically happy. When we talk about their motion, they are highly mobile. They are forming transient hydrogen bonds with adjacent water molecules. These transient hydrogen bonds form and break on the picosecond time scale. So these water molecules have high entropies. And what I mean by that is they are mobile. They have much translational and rotational freedom. They are able to move around. But now, I introduce a nonpolar solute. And on the right-hand side here, this is a lipid. Actually, it's a fatty acid, but we will talk more about this later in the course. Fatty acids have a distinct polar head group, as we will call it, and a nonpolar tail. Usually this is a nonpolar alkyl tail. It can be completely unsaturated or saturated, but nonpolar nonetheless. So what you're going to see is that hydrogen bonding interactions can form with the head group. As shown, this is a carboxylate, so you have two polar oxygens that can easily form hydrogen bonds with water. But the rest of the molecule cannot. You have a nonpolar alkyl group where there is not the potential for hydrogen bonding. So what happens, because this molecule still must occupy space in solution, water molecules basically part and they form an ordered so-called cage around the nonpolar functional group. So here, these water molecules are not directly interacting with the nonpolar aspect, the nonpolar part of the molecule, but they still have to form an ordered hydration shell around the nonpolar part. So you'll see, these water molecules are interacting with each other, and they become more ordered. So there is an entropic cost to hydrating a nonpolar molecule that is not offset by other interactions that may form. I already told you that normally a polar molecule, a polar solute, is going to compensate for the entropic penalty of disrupting hydrogen bonding by forming new solute water hydrogen bonds that are more favorable that offset this. Here, you don't have any solute water hydrogen bonds, but you still have the entropic penalty. So these waters are ordered as they surround the nonpolar part, and so this occurring without any solute water hydrogen bonding leads to an entropic penalty to dissolving a nonpolar solute in water. Hence the commonly observed phenomenon of forming two layers. You have your oil layer and your water layer, and this is a consequence of entropy, really. If we take a brief look at the thermodynamics of transferring hydrocarbons, nonpolar molecules, from water into nonpolar solvents, you'll get a feel for the fact that the hydrophobic effect is driven primarily by entropy. So if we look at this table 2.2 here, you'll see in each case you have something nonpolar. So in this first one, methane, ethane here, or benzene, toluene. We start out in water in all cases, and what we're looking at is the transfer of the nonpolar solute back from water into nonpolar solvent. Okay, so to say that one more time, we are transferring a hydrocarbon from water to nonpolar solvents, and what we're looking at here are the thermodynamic parameters, enthalpy, entropy, and delta G for each of these reactions, each of these transfer events. So you'll see that the enthalpy change is not dramatic for these events. In fact, in some cases, the change is zero. So this is clearly not an enthalpically driven process, which should make sense. You're not really forming interactions with water, or you're not breaking interactions with water, because those interactions never occurred in the first place. But what you are doing is changing the ordering of water in the original system. So remember, the hydrophobic effect involves the ordering of water molecules around your solute, but you don't have significant interaction via hydrogen bonding or non-covalent interactions between your nonpolar molecule and water, hence the lack of change in enthalpy. So when we take our nonpolar molecules and move them from water into nonpolar solvents, water that was previously disordered, rather, let me state that again, water that was previously ordered around the nonpolar solute now can become disordered again. It doesn't have to move, doesn't have to order to accommodate the nonpolar solute anymore. So when we look at this, you'll see our entropy changes are very good. In fact, this reflects a very favorable thing. And I should highlight here, this is shown as minus T delta S, but what you should notice here is the magnitude. So the takeaway message here is that the entropy increases for the system, increases when your nonpolar solvent or nonpolar molecule leaves an aqueous solution. So here you have very favorable entropy changes. The enthalpy change, not a whole lot, but you should note here that the overall delta G's for each of these events is negative, and this is driven by my large change in entropy. Now, if we remember that thermodynamics should be reversible, what this also tells us is that entropy must decrease when the nonpolar molecule enters water in the first place. So if you just change the sign around here, you'll notice that you have an entropic increase when a nonpolar molecule leaves aqueous solution, but entropy must decrease when the nonpolar molecule enters water in the first place. So when we look at the thermodynamics, I want you really to understand that the hydrophobic effect is an entropic process. It is driven by entropy. If the hydrophobic effect is, in fact, entropy driven, and that entropy cost is paid by the ordering of water molecules, we now have two different scenarios that we have to consider, where one of these scenarios allows for the minimization of that entropic cost. I'm sure that you have seen this. If you add some oil into water, you're probably going to observe emulsions form. Okay, so what that should tell you already is that lipids, nonpolar molecules, tend to cluster when introduced into aqueous solution. This is a way to minimize that entropic cost that we're talking about. Okay, so let me explain this. First, let me give you the big picture here. Multiple nonpolar molecules tend to cluster together because their joint solvation cage involves less surface area and therefore fewer ordered water molecules than in separate cages. Okay, so that sounds a bit technical and jargony, so let me break this down for you. If we look at this situation, this scenario on the left-hand side here, what we're talking about is the hydration of individual nonpolar molecules. So you'll see one nonpolar molecule, one here, so 3 fatty acids altogether. And in each case, water molecules have to part and basically order around the nonpolar segment within each of these molecules. Okay, so we need to start thinking about this in terms of surface area. Each of these molecules has a defined surface area. The nonpolar group here is going to be described by some surface area, and that surface area is important because that directly dictates how many water molecules must order around that nonpolar part. Okay, so what I'm telling you is, if I made this nonpolar part of the molecule larger, the surface area of that nonpolar segment also increases, and I have to order more water molecules to compensate for the increased surface area. And now I have 3 molecules, so increase that, basically multiply that surface area by 3, and you'll see that you have 3-fold more water molecules that have to become ordered to hydrate, to allow for suspension of these nonpolar molecules in water. Okay, so this is in fact not what we see though. The fact that you observe an emulsion means that your nonpolar molecules actually cluster together. So if we look at the clustering case, this is shown on the right hand side, you'll see those same 3 molecules cluster together, and instead of individually hydrating each of your solutes, each of your nonpolar solutes, the water molecules cluster around the nonpolar exterior. So basically you have a defined peripheral surface area that is surrounded by ordered water molecules. So in reality, the clustering of nonpolar molecules leads to an overall decreased surface area that has to be surrounded by water molecules. So the individual clustering, the individual hydration case shown on the left-hand side actually yields a higher surface area than the clustering case shown on the right-hand side. So if surface area is directly related to the number of water molecules that have to become ordered to allow for suspension in water, the clustering case shown on the right-hand side would require fewer ordered water molecules. Therefore, the entropic cost of the left-hand case versus the right-hand case is such that the cost is lower when the nonpolar molecules cluster together. So this all comes back to thermodynamics. Here, the entropic cost, the entropic penalty, is lower if the nonpolar molecules come together to form these so-called clusters. Now I want to introduce you to amphiphils. An amphipathic compound contains regions that are polar or charged, as well as separate regions that are nonpolar. If we look at the examples I'm showing you here, you will see distinct hydrophobic tails, so these are nonpolar alkyl tails, and polar head groups. So dodecyl sulfate, you'll often find this in soaps like shampoos. This is often referred to as sodium dodecyl sulfate. It's a very good detergent. Palmitate often shows up too, but in both cases you have, again, non-polar alkyl tails. These are referred to as hydrophobic tails, as well as these polar functional groups that we call the polar head groups. So when an amphipathic compound is mixed with water, the polar hydrophilic region interacts favorably with the water and tends to dissolve, but the non-polar hydrophobic region tends to avoid contact with the water. The non-polar regions of the molecules tend to cluster together via the hydrophobic effect, and this presents the smallest hydrophobic area, think surface area, to the aqueous solvent. The polar regions are then rearranged to maximize their interaction with the solvent. So this overall phenomenon is the hydrophobic effect that we are talking about, and these structural rearrangements to maximize exposure of polar groups to water and minimize exposure of nonpolar groups to water. These are going to lead to very unique overall structures, and we'll talk about those in a moment. These structures I'm telling you about, remember, they are the result of a system achieving the greatest thermodynamic stability by minimizing the number of ordered water molecules required to surround the hydrophobic portions of your solutes. So this is a thermodynamic problem. Now, the way that we go about doing this, these amphiphiles in solution, they can adopt multiple structures. And this relates to how water hydrates the hydrophilic portion relative to the hydrophobic portion. So in one case, we can form micelles. So this is a micelle here. Remember, you have a polar head group and a nonpolar hydrophobic tail for your nonpolar molecules. So here, the micelle is more or less a spherical structure that positions those polar head groups on the exterior. So you have basically a polar exterior and a hydrophobic interior. So by positioning all of your polar head groups to interact with water, you've more or less excluded the hydrophobic portion and made it such that it doesn't interact with water. Now, there are other possibilities too. You can form bilayers as well, where you have polar head group and you have a non-polar interior. Now, here you have two separate monolayers. So here's this top layer. This is a monolayer, and another monolayer. These come together to form the bilayer. Now you'll notice that there are ends. So here we're looking at one end. If you looked at it from another angle, there's another end. There are non-polar groups that are exposed to water. In reality, what's going to happen for a bilayer usually is if you extend this out, it's going to fold back around and form a larger structure that may in fact resemble a micelle. Now, one thing to point out here, if I took the same molecule, here I have nonpolar molecules that have hydrophobic tails and polar head groups. If I took this same solution, this same molecule, and put it into a nonpolar solvent, what I would actually see is that my micelle, my bilayers, would react and more or less invert in structure. So a micelle, when in a nonpolar solvent, actually forms a spherical structure still, but the polar head groups are on the interior and nonpolar tails are pointed outward towards nonpolar solvent. So remember here, this is a thermodynamic problem that is in aqueous solution, an effort to minimize interaction of nonpolar portions of your molecules with water. This is all an attempt to minimize the requirement for ordering of water molecules around your nonpolar solute. Now, because this is a thermodynamic problem, it should all relate back to the thermodynamics, the free energies of this process. There is a parameter for any detergent, any nonpolar molecule, called the critical micelle concentration. This is the concentration of detergent at which you promote 50% micelle formation. So this relates back to the point at which the conditions at which the individual solvation of your detergent becomes unfavorable. Now, I'm not really doing justice to this parameter just yet. You'll see later on when we talk about lipids, you'll see this in more detail. But what I want you to really understand is the adoption of these structures, these three-dimensional structures, is a response to thermodynamics. This is a thermodynamic challenge. So you're going to see in this course many three-dimensional structures and just general behaviors of enzymes relate back to thermodynamics. So you can't, unfortunately, escape thermodynamics here. Here we have a summary of the common non-covalent interactions that you can expect to see among biomolecules in aqueous solvent. You'll see hydrogen bonds here, ionic interactions, the hydrophobic interactions, as well as van der Waals interactions. These are the four big types of non-covalent interactions that you can expect to observe. Now, you should know at this point that hydrogen bonding is perhaps going to be the most important of the non-covalent interactions. In fact, in 1939, Linus Pauling proposed that hydrogen bonding would be the most significant non-covalent interaction of these. Now, we have to talk a little bit more about contributions here. You should remember that these are non-covalent interactions. These are going to be weaker interactions relative to covalent bonding. As a reminder, an input of about 350 kilojoules of energy is required to break 1 mole of carbon-carbon single bonds. About 410 kilojoules is required to break 1 mole of carbon-hydrogen bonds. In contrast, as little as 4 kilojoules is sufficient to disrupt 1 mole of a typical van der Waals interaction. So interactions that are driven by the hydrophobic effect are also much weaker than covalent bonds, though they are strengthened substantially when in polar solvent. Say, a concentrated salt solution will really make the hydrophobic effect more pronounced. Ionic interactions and hydrogen bonds themselves are variable in strength. They're going to depend upon the polarity of the solvent as well as the alignment of the hydrogen bonded atoms, so the alignment of your hydrogen bond donor and acceptor. However, they are always weaker than covalent bonds. In aqueous solvent at 25 degrees Celsius, the available thermal energy can be of the same order of magnitude as the strength of these weak interactions. The interactions between solute and solvent molecules, so water molecules, is nearly as favorable under these conditions as solute-solute interactions. Consequently, hydrogen bonds, as well as ionic, hydrophobic, and van der Waals interactions, are continually forming and breaking under physiologic conditions. So you should consider this, these non-covalent interactions to be transient in nature. They form, they break, and what you're looking at is a network effect. When we talk about these non-covalent interactions, we say, oh, they're weak. But what you have to think about is that when we are talking about them in the context of stabilization of three-dimensional structure of any biomolecule, this structure is never the result of a single interaction. It is a network effect. There are multiple non-covalent interactions occurring simultaneously. So these can be hydrogen bonds, ionic interactions, hydrophobic effect, van der Waals interactions. These all four of these non-covalent interactions are contributing to the overall three-dimensional structure for a biomolecule. This is a network of interactions. So the network leads to significant stabilization of overall structure. So yes, these non-covalent interactions are weaker than covalent bonds, but they are still significantly stabilizing when used as a network. You will see many examples of this as we proceed through this course, but I want to really highlight the importance of water in stabilization of three-dimensional structures. So macromolecules, you'll hear me use this language. What this refers to are biological molecules like protein, DNA, RNA. Macromolecules form their three-dimensional structures using a network of many different kinds of non-covalent interactions. So these are interactions that are drawn from the 4 common interaction types that we just talked about: hydrogen bonding, ionic, van der Waals, as well as hydrophobic interactions. So for macromolecules, the most stable structure is going to be one in which all of these weak interactions are maximized. These weak interactions are forming a network that overall contribute to the stability of the structure. Now, going forward, we're probably going to dwell a lot on the intramolecular or interactions, so mostly intramolecular interactions or interactions between biological molecules, but we may not talk as much about the role of water. And we're not going to spend a lot of time talking about water here either. But what I want to highlight to you is that water is an integral part of this structural stabilization. Here, you're looking at the structure of hemoglobin. So on the left-hand side here, panel A, this is hemoglobin with waters highlighted. So these are water molecules that were experimentally determined alongside the protein structure. You'll see water molecules coat the exterior of the protein. And if you remove those waters, this is what you have on the right-hand side. What I want to highlight here is that these water molecules are bound so tightly to hemoglobin that they're actually considered to be part of the structure. You can also see this in structures for RNA as well as DNA. These bound water molecules, they can be detected experimentally by methods like NMR, nuclear magnetic resonance, or X-ray crystallography. And these water molecules have distinctly different properties from those of bulk water. And so what I mean by that, if you think about entropic descriptions or general interactions, they behave differently than they would free in solution. Now, these water molecules are contributing in ways that I have highlighted earlier. So in part 1, I showed you how waters may contribute via stabilization of protein-protein interactions or bridging effects. So I just want you to remember that water is a critical part of not only solubilizing biological molecules, but also stabilizing the overall three-dimensional structure. In addition to three-dimensional structure, waters can also facilitate catalysis. And I've already talked about instances early on where you have activation of water molecules to function as nucleophiles, but they can also play other roles. So here I'm showing you a schematic of cytochrome F. You will notice that there are 5 water molecules, 1, 2, 3, 4, 5, that are present in this structure. So first, cytochrome F, it plays a role in the energy trapping machinery of photosynthesis in chloroplasts. So it's important for movement of protons. That is its contribution, or one of its contributions here. If you look at the water molecules, you'll see that they actually bridge amino acid features. So you have an amide functional group that comes from the amino acid asparagine. This interacts with the water, which is bridged to another amide group of another amino acid. You'll see a lot of functional groups that are bridged here. But one of the other roles, in addition to the structural stabilization that you see here, is the potential for proton hopping. So electron flow, remember in photosynthesis we're moving electrons around here. Electron flow there is coupled to the movement of protons across a membrane. And this involves what is referred to as proton hopping. So these water molecules, they can facilitate this proton hopping where if you transfer a proton to a water, you generate a hydronium ion. And often you'll see proton hopping where a hydronium basically transfers a proton to an adjacent water, which then transfers to an adjacent water, and so on and so forth. So protons can be shuttled through over a certain distance via this proton hopping or proton shuttling effect. So the waters that you're seeing here in cytochrome F, they are going to be important for structural stabilization as well as facilitation of the catalytic function of this enzyme. Solutes of all kinds alter the physical properties of the solvent, in this case water. The properties that we're talking about here are vapor pressure, boiling point, melting and freezing points, as well as osmotic pressure. Together, these properties are referred to as the colligative properties. The term colligative means tied together, so you have basically one cause that is impacting multiple properties. And so here what we're talking about is really the influence of solutes on the properties of water. Now, as we have talked about, the presence of a dissolved substance, a solute, it disturbs the structure of liquid water. Whether you have a nonpolar solute or a polar solute, you get a disruption to the structure of liquid water. You have to have then waters of hydration that order around your solute. So it doesn't matter if it's a nonpolar or polar solute, there has to be ordering of water around if those solutes are going to go into solution. Now, this ordering of water around your solute disrupts the structure of liquid water. The way that this occurs may involve different paths. So your ions are going to establish hydration shells that involve solute solvent interactions. Hydrophobic molecules simply force an ordering of water molecules without those interactions. But in both cases, we disrupt the overall structure of liquid water. This is important because the commonality here that whether polar or nonpolar, a solute disrupts the structure of liquid water. This is important because what this means is that independent of solute properties, or rather solute polarity, the solvent properties are going to depend only on the number of solute particles per unit volume, so the concentration of solute particles present. The solvent properties do not depend upon the chemical nature of the solvent because the effect of the solvent is the same. Whether polar or nonpolar, you are disrupting the structure of liquid water. So it doesn't really matter what kind of solute you have. What matters is how much solute you have. How many molecules, how many particles of solute do you have? Now, the effect, we're interested in the effect here. So the effect is that solutes are going to depress the freezing point. When we freeze something, you need to be able to adopt an ordered crystalline lattice. So water molecules want to come together to form the ordered crystalline array that we talked about in previous discussions here. Now, if you have solutes in there that are disrupting water-water hydrogen bonding, you're going to make it harder to freeze. You're going to make it harder to adopt an ordered crystalline lattice. So therefore, the freezing point actually goes down when solvent is present versus when it is not. In contrast, we're going to see an increase in the boiling point of water as well. And this is because the solute-solvent interactions are actually stronger than the water-water interactions alone. So you make it harder. You have to put in more energy to disrupt all hydrogen bonds for a given water molecule when, say, an ion is present versus when it is not. And this makes it harder for your water to escape into the gas phase. So these are very important things to understand, that the water properties are going to be perturbed by the presence of a solute.